So I want you to try and close your eyes for a second. Assuming you aren't driving right now, obviously.
Yeah, please keep your eyes on the road if you're driving.
Right, safety first. But if you can, imagine you're standing on the sunny shores of the Mediterranean Sea. Maybe, I don't know, you're in southern Spain or looking out from the rocky coast of Italy.
It's a gorgeous image.
It is, right. But instead of that sparkling, beautiful blue water stretching out to the horizon, you are staring down into a canyon. Just a completely dry, blindingly white, salt-crusted canyon.
And it goes deep.
Oh, kilometers deep into the earth. The air is unimaginably hot, it's thick, and honestly, it looks less like a vacation destination and more like, I don't know, the surface of an alien planet.
Which is wild to think about because that alien landscape isn't science fiction at all.
Exactly. 5.33 million years ago, that was the actual reality of the Mediterranean basin. And for today's deep dive, we are exploring a single Wikipedia article about a truly terrifying geological moment called the Zanclean Flood.
It's just such a monumental event.
It really is. It's the moment when the Atlantic Ocean broke through a rocky dam and basically swallowed that entire desert whole. I mean, it forever altered the physical geography, the climate, and the biology of the whole planet.
It is a really profound image to hold in your mind. Just to think that one of the most famous bodies of water on Earth, this massive inland sea that completely shaped human civilization, it spent hundreds of thousands of years as a baking dust bowl.
Right, just a giant empty pit.
Yeah. We are looking at an event of sheer, almost incomprehensible scale today, where an entirely dry basin turned back into a massive sea, potentially in a matter of, months.
Which just breaks my brain a little bit, but to understand the physics of how a flood of that magnitude even happens, we kind of have to look at the before picture first, right?
Exactly. And that before picture is fundamentally a story of plate tectonics.
Because millions of years prior to this whole desertification thing, the Mediterranean wasn't an isolated basin at all.
No, not at all. It was actually part of a much larger ancient body of water called the Tethys Ocean.
Right. But, the Earth's crust is always in motion. So you had this massive tectonic vice grip forming. The African plate, the Arabian plate, and the Eurasian plate were all just slowly grinding together. And this immense tectonic pileup gradually shrank that Tethys Ocean until its westernmost part became what we now recognize as the Mediterranean basin.
And crucially, even after it took that basin shape, it actually remained connected to the global ocean for a long time.
Oh, right, through those ancient waterways.
Yeah, it exchanged water with the Atlantic through these corridors known as the Guadalhorce and Riffian corridor.
The Guadalhorce and Riffian. Got it.
But then, during the late Miocene epoch, the local geology shifted. And whether it was tectonic uplift pushing the land higher or maybe a global drop in sea levels, those corridors eventually closed.
Just pinched shut.
Completely.
Right.
The Mediterranean was severed from the Atlantic Ocean, shutting off its primary source of water.
Which sets up a massive thermodynamic problem. I mean, the Mediterranean sits at a latitude where it receives really intense solar radiation.
Oh, absolutely. It's hot.
Right. So the atmospheric conditions dictate that evaporation is just incredibly high. Once you cut off that constant top-up from the Atlantic, the local rivers and the rainfall simply cannot keep pace with the sheer volume of water being vaporized by the sun.
They can't even come close.
Yeah, so the basin starts operating at a massive water deficit.
And the math of that deficit is staggering. I mean, water levels didn't just drop a few feet. They dropped by kilometers.
Kilometers, just imagine that.
Yeah, and this triggered a period known as the Messinian salinity crisis. Because, seawater contains about 35 grams of dissolved salts per liter.
Right.
So when you vaporize millions of cubic kilometers of seawater, that mineral payload doesn't just vanish into the sky. It precipitates out.
It has to go somewhere.
Exactly.
Yeah.
The crisis left behind these halite and gypsum deposits on the former seafloor. They were literally kilometers thick.
Kilometers of salt. And dropping the sea level by over a mile fundamentally changes the geomorphology of all the surrounding continents, too. I was reading in the source material about the major rivers, like the Nile and the Rhone.
Oh, yeah, the rivers go crazy.
Yeah, because when the sea level plummeted, these rivers suddenly found themselves flowing off incredible continental precipices.
Right, because in hydrology, there is this concept called base level. It's basically the lowest point to which a river can flow, which is usually sea level.
Makes sense.
And a river will relentlessly erode downward until it meets that base level. So when you lower the Mediterranean by thousands of meters, the rivers feeding into it suddenly gain a terrifying amount of gravitational potential energy.
They transform from these meandering waterways into, like, geological chainsaws.
That's a great way to put it. The ancient Nile, seeking its new, severely lowered base level, carved a canyon into North Africa that makes the Grand Canyon look totally modest.
Wow. But let's unpack the reality of that basin floor a bit, though, because
Right.
it wasn't a uniform, bone-dry desert everywhere.
Right. No, it wasn't.
I think it's best to think of it like pulling the plug on a giant bathtub where the tap is still dripping just a little bit.
Yeah, that's a good analogy.
Because there was still a slight influx of Atlantic water seeping in, plus whatever river runoff and rain the region did actually receive. This created these lower salinity remnant seas in the deepest depressions.
Right, known as the Lagomare.
The Lagomare. But having these isolated hypersaline lakes scattered across this dark, deep basin floor sets up a highly precarious physical situation.
Because you have a massive vertical void in the Earth's crust, sitting right next door to the entire Atlantic Ocean. And they are separated only by a narrow land bridge at the Strait of Gibraltar.
Just a wall of rock holding back an ocean.
Exactly. The Atlantic is exerting an ungodly amount of hydrostatic pressure against that rock. The whole system is just loaded with potential energy waiting for a structural failure.
Which brings us to 5.33 million years ago, marking the start of the Zanclean Age and the beginning of the Pliocene epoch. The dam finally breaks.
It does.
But looking at the geological record, it wasn't necessarily like a massive earthquake that shattered the rock all at once, was it?
No, and that's a common assumption.
Yeah.
Tectonic subsidence is one hypothesis, sure, but the most widely supported mechanism among geomorphologists is something called headward erosion.
Headward erosion. Okay, what does that look like?
Imagine a small stream flowing eastward down the steep slope of that land bridge, right down into the deep, dry Mediterranean basin.
Okay, I'm picturing it.
Because of that extreme vertical drop we discussed, the stream flows with immense force, and it actually erodes the rock backward, cutting into the land bridge from east to west.
Oh, wow. So it's eating its way uphill, basically.
Exactly. Over thousands of years, this little stream relentlessly carved its way backward until it eventually reached the Atlantic Ocean, breached the threshold, and just captured the sea.
That is wild. A tiny stream eroding backward until it literally unzips an entire ocean. And once that initial breach occurred, the fluid dynamics described in the modeling data are just staggering. We are talking about water rushing down a 1,000-meter drop. At its peak, the discharge was 100 million cubic meters per second.
Right. And in oceanography, volume transport is measured in this unit called sverdrups.
Sverdrups.
Yeah. One sverdrup is 1 million cubic meters per second. The Zanclean Flood reached 100 sverdrup.
100.
To put that catastrophic volume into perspective, the total outflow of all the rivers on Earth today combined is only about 1.2 sverdrup.
For everyone listening, let that number sink in. 1.2 for all modern rivers. This single localized flow was 100. It was roughly 450 times larger than the current discharge of the Amazon River.
It's just massive.
It was 10 times bigger than the massive Missoula floods that carved up North America at the end of the last ice age. The sea level in the Mediterranean basin was rising by 10 meters, so more than 30 feet every single day.
You could literally sit on the hillside and watch the ocean swallow the land in real time.
That is terrifying.
But we do need to correct a pretty persistent misconception about how that water actually entered the basin, though.
Oh, really?
Yeah, because when people hear 1,000-meter drop, the immediate visualization is a giant sheer waterfall, like a localized Niagara Falls, but 1,000 times bigger, crashing straight down into an abyss.
Well, yeah, I mean, that's the most intuitive mental image when you hear those dimensions.
It is, but studies of the seismic reflection profiles and the underground structures at the Strait of Gibraltar show a very different hydrodynamic reality.
Okay, so what did it look like?
The flooding channel actually descended quite gradually toward the bottom of the basin. It wasn't a vertical cliff at all. It was a massive, relatively gentle ramp stretching over tens of kilometers.
Okay, though, to be fair, the word gentle is doing a lot of heavy lifting there, because considering the water moving down this ramp was traveling at about 144 kilometers per hour, or roughly 40 meters per second.
True, gentle is relative. And that velocity changes everything about how the water interacts with the rock. Water moving at 40 meters per second doesn't just flow over a landscape. It operates like an industrial water jet cutter.
Oh, man.
The sheer velocity turns the water itself into a blade capable of mobilizing solid bedrock. The current carved a massive U-shaped channel, right into the seafloor of the Alboran Sea, which is the westernmost part of the Mediterranean.
And a U-shaped channel is usually the classic signature of a glacier, right? Not a river.
Exactly.
Rivers typically cut V-shapes, so the fact that liquid water cut a U-shape tells you the flow was so voluminous and so turbulent that it acted with the solid, bulldozing mass of a glacier.
It did. It ripped up an estimated 1,000 cubic kilometers of solid rock.
1,000 cubic kilometers.
And that material was carried by the current and dumped further into the Alboran Sea, forming these giant submarine bars that we can actually still detect under the Pliocene sediment today.
But that velocity creates a massive kinetic problem when the water runs out of room, because the Mediterranean isn't just a single open bowl.
No, it's not.
It's structurally divided into two main basins, west and east. And standing right between them was a massive internal wall known as the Malta Escarpment, located near the present-day Straits of Sicily.
Right, so the initial breach of Gibraltar only fills the western Mediterranean at first.
Okay.
But because the water is rising 10 meters a day, it doesn't just, gently lap against that internal wall when it reaches it.
Smashes into it.
It hits the Malta Escarpment, tops it, and sets the stage for a second. Localized mega flood. The water violently spilled over this internal barrier through a submarine channel called the Noto Canyon, right off the coast of Avola, Sicily.
Wow.
And it cascaded into the deep Ionian Sea of the Eastern Basin. The localized effects of this second spillover were just pure chaos.
I can only imagine.
The kinetic energy generated massive whirlpools, terrifying reverse flows, and it blasted immense amounts of sediment into the Ionian Sea. The magnitude of this internal spillover was physically comparable to the initial flood at Gibraltar.
Which forces us to look at the physical toll on the Earth's crust itself. Because, you can't just introduce billions of tons of hydrostatic load onto a tectonic plate in a matter of months without breaking the local equilibrium, right?
But no, you absolutely cannot. The phenomenon you are pointing to is called induced seismicity. And it relies on the principle of isostasy.
Isostasy.
Yeah. The Earth's rigid outer crust is essentially floating on the semi-liquid, highly viscous mantle below it.
Okay.
During the hundreds of thousands of years of the Messinian salinity crisis, billions of tons of water weight had evaporated. So in response to that missing mass, the crust slowly rebounded upward.
Because the mantle below had time to slowly flow inward and push the lighter crust up.
Precisely. But the Zanclean Flood throws all that immense weight back onto the crust almost instantaneously, at least in geological terms.
Oh, I see.
The mantle is viscous. It cannot flow out of the way fast enough to accommodate the sudden, massive downward pressure. So the crust literally fractured and shuddered under the strain, triggering substantial earthquakes.
And massive sudden earthquakes underwater translate directly to displacement of the water column, which means tsunamis.
Exactly. The seismic shaking destabilized the steep continental slopes that had been carved out when the basin was dry. This led to massive underwater landslides, which displaced enormous volumes of water, generating mega tsunamis.
Jeez.
Sedimentological evidence found in the Algeciras Basin suggests these tsunami waves reached heights of 100 meters.
A 300-foot wave rebounding around a rapidly filling basin. That is just apocalyptic.
It really is. The tectonic stress from the sheer weight of this new sea was so profound that it rippled through the regional plates. It actually physically influenced the development and uplift of the Apennine Mountains in Italy.
Wait, really?
Yeah. The localized gravity field of the Earth itself was being altered by the infilling of the sea.
That is unbelievable. But, looking at the sources, we should be clear that this catastrophic one big swoosh model isn't universally accepted by every single geologist.
That's true, it's not.
Because if the whole basin filled in just 2 years with that level of extreme violence, we would expect to see uniform, chaotic sediment deposits everywhere. Yet the data from the North African margin tells a slightly quieter story, doesn't it?
It does. It is a very vibrant scientific debate. And the dichotomy in the geological record is fascinating. The catastrophic model is heavily supported by those chaotic sediment deposits around the Malta Escarpment we just talked about,
Right.
which strongly imply an incredibly intense, rapid flooding event. However, researchers examining the southern margin of the Alboran Sea near North Africa, they find sedimentary layers that suggest a more gradual reflooding.
Okay, so it suggests the Mediterranean might have resealed in multiple smaller pulses over a longer period, perhaps involving like an intermittently open Strait of Gibraltar that allowed water to flow in, get restricted, and flow in again.
Exactly. The physical scars of a monumental flood are undeniable, but mapping the exact timeline...
Whether it was months or centuries.
Right. Whether the bulk of the water rushed in over a few months, a decade, or a couple of centuries, that is the puzzle the scientific community is still actively piecing together today.
And obviously we aren't taking sides here. We have to impartially weigh both the chaotic deposits in the north and the stratified deposits in the south. We're all just trying to read the same 5 million-year-old rocky diary.
Well said.
But regardless of whether it took 2 years or 200 years, in the grand sweep of geological time, it is an instantaneous geographic transformation. And that transformation forced a total biological reset.
It was a massive shock to the system.
Let's talk about the biosphere, because the immediate shocks were absolute. For hundreds of thousands of years, the dry Mediterranean basin acted as a massive terrestrial superhighway.
Oh, yeah.
Land animals, early mammals, and reptiles could freely cross back and forth between the continents of Africa and Europe.
But the formation of the Strait of Gibraltar permanently shattered that migration route. The terrestrial gene flow between Europe and Africa was abruptly severed, which fundamentally altered the evolutionary trajectories of species on both continents.
Right.
It is a textbook trigger for allopatric speciation, where isolated populations diverged genetically.
And nowhere is that allopatric speciation more intense than on the high ground that suddenly became islands.
Very true.
Places like Crete or Cyprus were just mountains in the dry basin. But when the floodwaters rose, they became islands, trapping whatever animals and plants just happened to be on them at the time.
And those newly formed islands became evolutionary pressure cookers. When terrestrial animals are suddenly confined to an island with limited resources and, crucially, no new predators, they often undergo rapid morphological changes.
Okay, what kind of changes?
It's governed by what evolutionary biologists call Foster's rule. You see instances of island dwarfism, where large mammals shrink to survive on fewer calories. And on the flip side, island gigantism, where small animals grow unusually large in the absence of predators.
That makes a lot of sense. The sources specifically highlight incredible localized adaptations, like the evolution of the Greek marsh frog, directly tied to this event.
Yeah, the biology is fascinating.
And the flora had to endure a massive shock to the soil chemistry, too. The genome of coastal plants, like modern watercress, actually still retains the genetic evidence of the rapid adaptations that were required to survive the sudden, massive influx of marine saltwater into their environment.
It's amazing that we can still read that history in their DNA.
Right.
And while the terrestrial flora and fauna were violently isolated, the marine biosphere experienced the exact opposite.
A completely new frontier.
Exactly. The newly opened gates at Gibraltar provided an unprecedented opportunity. Marine life surged in from the Atlantic. Cetaceans, so the ancestors of modern whales and dolphins, and pinnipeds, like ancient seals, they suddenly had this entirely new, vast, empty, nutrient-rich sea to colonize. It was a completely blank slate for marine ecosystems to claim.
But pouring an ocean's worth of water into a new basin doesn't just change the local biology. It changes the entire planet's operating system.
It does.
The Zanclean Flood likely altered the global climate, which seems counterintuitive at first. Like, how does filling one regional basin, even a massive one, change the weather in the southern hemisphere?
Well, the mechanism lies in the Earth's thermohaline circulation.
The ocean currents.
Right. The global oceans are a deeply interconnected conveyor belt of currents driven by gradients in temperature and salinity, which we call the AMOC, or the Atlantic Meridional Overturning Circulation.
AMOC, got it.
And this conveyor belt regulates heat distribution across the entire planet.
So when you suddenly divert 100 sphere-drop of Atlantic water into the Mediterranean, you are actively stealing volume from the Atlantic and changing its overall salinity dynamic.
Exactly. You disrupt the AMOC. And if you disrupt that conveyor belt, you disrupt global heat distribution.
Wow.
We have actually seen similar mechanics play out in more recent geological history.
Yeah.
For example, when Lake Agassiz, which was a massive glacial lake in North America, rapidly drained into the Atlantic Ocean at the end of the last ice age.
Oh, right.
The sudden influx of fresh water altered the salinity so severely that it choked the ocean currents and triggered a sudden global cold period known as the Younger Dryas.
And the Zanclean Flood was moving an astronomically larger volume of water than that, so the global shifts would have been profound. I mean, the sources hypothesize that the remote environmental effects of this event reached incredibly far.
Very far.
With detectable shifts in ocean chemistry as far away as the Loyalty Ridge, which is situated near New Caledonia in the southwest Pacific Ocean.
Yeah, halfway across the globe.
We are talking about a flood in Spain and North Africa changing the ocean dynamics near Australia. That is wild.
It perfectly illustrates how sensitive the Earth's climate systems are to rapid changes in ocean volume and circulation.
It really does. But bringing it back to the local geography for a second, there's one detail in the sources regarding the aftermath of the flood that entirely rewrites how we picture the ancient landscape.
How about the rivers?
Yeah. We talked earlier about how rivers like the Nile carved deep canyons thousands of meters down into the bedrock when the sea was dry. Well, when the Zanclean Flood happened, the sea level rose to its current height, and those massive deep canyons filled with seawater as well.
Right. In geomorphology, a flooded river valley that remains open to the sea is called a ria.
A ria. And the deeply incised Nile River became a ria, stretching incredibly far inland. The ocean water flooded the canyon all the way to Aswan.
Which is just, it's so far inland.
That is 900 kilometers upstream from the modern Egyptian coast. Imagine a deep-sea harbor, an ocean inlet, reaching almost 1,000 kilometers straight into the heart of the North African desert.
It forced the ocean deep into the interior of the surrounding continents, creating marine environments in places that are now hundreds of miles from the nearest beach.
Right.
The Zanclean Flood wasn't just a matter of filling a geographic bowl. It was a total re-engineering of the intersection between land and sea.
It is truly one of the most dynamic events in our planet's history.
Yeah.
A dry, baking, salt-crusted canyon became the life-filled Mediterranean Sea we know today in a geological blink of an eye.
It's incredible.
And what is deeply fascinating to me is the historical irony of how humanity came to understand this. Long before we had seismic reflection profiles or sediment cores, the Roman author Pliny the Elder wrote about a legend.
The Hercules myth.
Yes, the myth stated that the hero Hercules dug the Strait of Gibraltar with his bare hands, physically ripping the mountains apart to connect the Mediterranean to the Atlantic Ocean.
It's so interesting because ancient cultures inherently recognized that the geography of the strait looked unnatural, like a breached wall. So they created a myth to explain a very real geographic anomaly.
But it wasn't until the 1970s that modern science actually pieced together the real story. Geologists drilling into the seafloor found those massive salt deposits we discussed, along with widespread erosion surfaces buried deep under the mud. And they finally realized that the myth of a catastrophic sudden connection wasn't actually that far off from the scientific truth. Nature's version of the breach was just infinitely more powerful than the mythological strength of Hercules.
It is a beautiful example of how empirical science often uncovers truths that are stranger and, frankly, far more magnificent than our oldest legends.
Definitely. And, to leave you with a final thought to mull over today, the Strait of Gibraltar, that relatively narrow, incredibly deep gap of water, is the only physical thing keeping the Mediterranean from evaporating and drying up all over again.
That's right.
Because the thermodynamic deficit still exists. The tectonic plates are still moving.
The African plate continues to push northward. The geological forces that closed the strait 6 million years ago, they haven't ceased.
Right. They are still happening. And knowing how delicate that balance is makes a piece of 20th century history deeply unsettling to me.
Oh, you mean Atlantropa?
Yes. In the 1920s, there was a seriously proposed, widely discussed engineering project called Atlantropa. The idea, which was spearheaded by a German architect, was to build a massive, real-world dam across the Strait of Gibraltar.
It's just unbelievable.
The goal was to deliberately block the Atlantic, allowing evaporation to lower the sea level of the Mediterranean by hundreds of meters.
And the intention was to create vast new tracts of land for settlement, and also to generate immense hydroelectric power as the Atlantic was allowed to just sort of trickle through the turbines.
They were essentially planning to artificially trigger a new Messinian salinity crisis. They wanted to manually reverse the Zanclean Flood.
That's crazy.
Just imagine the sheer, unadulterated hubris of that plan. What would it mean if humanity, rather than nature, actively chose to undo the most epic flood in Earth's history, intentionally bringing back the heat, the salt, and the dry, alien canyon we visualized at the very beginning of this deep dive?
It definitely puts things in perspective.
It makes you look at that sparkling blue water a little differently, doesn't it? Well, that's all for today's deep dive. Thanks for listening, and we'll catch you next time.